In this presentation, I'll be demonstrating a visual simulation for the n-body problem. The n-body problem is the complexity involved in predicting the movements of circular objects with masses. These objects are confined to an isolated space where each object is subjected to the gravitational force of all others. These objects with masses will be referred to as bodies hereafter. The software involved includes a header file and a source file that utilize the standard library, the GLOT library, and the OpenGL library. The header file consists of a convenient template class to hold the XY components of a vector and perform operations with it. This template class is used to hold the current states of a body, which includes its position, velocity, acceleration, and mass. This class has a couple necessary member functions. One function computes the oriented individual force enacted on one body by another. This member function computes the oriented distance between bodies. This member function updates the current state of a body according to the calculated net force. This member function assigns a radius to an object based on its mass and calculates the points that would lie on its circumference. This helper function handles cases where bodies collide. This will be explained further on. Within the time between frames, this helper function calculates the net gravitational force on each body with an optimized technique that avoids redundant calculations and reduces the number of loops. Also, this function checks if a body collides with another or reaches the edge of the object space/window. This RA2 class ensures that the memory reserved for each body is deallocated if the program terminates. This source file utilizes the classes and helper functions defined in the header file. The source file collects the input data and ensures all inputs are valid. It then creates a system of bodies. This section assigns the initial states to the corresponding bodies. This section ensures none of them initially overlap. The source file also utilizes the OpenGL and GLOT library to visualize the changes in the system. It initializes the library, sets the display mode, and window settings. It also provides the GLOT library with the display, reshape, and timer functions to use. The display function redraws circular objects for each body in each frame, where each object is placed in its current position with respect to the object space. The reshape function defines the object space based on the maximum value of initial positions amongst all bodies in the system. The timer function recursively calls itself 30 frames per second and performs the work needed to be done between each frame. To demonstrate the software, I'm visualizing a system with a gravitational constant of 7.32 times 10 to the minus 5. If I want to use the actual gravitational constant, I can set this input to 0 and the program will use the actual constant as a default. The program will use a time step of 20 seconds in its calculations. And the system will include 7 bodies. These are their masses, initial position, velocity, and acceleration. In the top directory containing the files for this project, the software can be built and installed with the following commands, where this would replace your installation directory. This command is used to run the demonstration. In the case of a collision, as you can see can happen frequently, this is handled by the mathematics involved in elastic collision, which assumes all collisions are head-on. The angle of impact is handled by comparing the direction of a body's velocity to the direction of the oriented distance to the other body involved in the collision. This reduces complexity, which is beneficial for the fast computations required between each frame. Notice that the effect of gravitational force is obvious, as smaller bodies are drawn to the bigger ones, and the smaller bodies typically move at a higher speed than the bigger ones.